want to go over over here, and this follows directly on the question that we just had. When you're doing remote sensing, you tend to look at a lot of things that look like this. Okay, this is spectral reflectance for 3 different things here. Dry, bare soil, green vegetation, and clear water. Okay? So what we're looking at here across this axis, oh good, it has blue, green, and red. We're looking up this axis right here. We're talking about the amount of reflectance in that particular part of the spectrum. Across here, we're talking about, we're going across the spectrum. Here's your wavelength of the light. Now, I noticed up here, this is really good on this one. So blue, visible blue light is just right there. Okay. And now green, that's the green band, and then the red. So visible light is something like this. Okay. And then here we go into the near infrared, and then over here into the middle infrared. So we're looking at stuff that we don't actually just see with our eyes. So let's look at, and this also helps to explain that image, which is why I was looking at this next. Here is clear water. Here's the reflectance of clear water. You can tell that actually it doesn't reflect a whole lot in anything. Let's take a look what happens. It doesn't reflect blue a whole lot. It doesn't reflect green a whole lot. It doesn't, pretty compared to the others. It doesn't reflect red a whole lot. And then once you get into the infrared, the reflectivity of water drops almost to nothing. Water happens to absorb infrared light very, very well. So if you hit a water body with infrared light, it absorbs it. Let's take a look. So it doesn't enter our collector. Remember, we only get things that are reflected. Of course, also when you're detecting the remote sensing of water, you also have the problem that, particularly in shallow water, you're probably getting stuff bouncing off the bed. Like you're trying to do remote sensing of rivers. You know, I'm not exactly sure how deep the water has to be to make sure that nothing is reflecting off the bottom. And what the bottom is composed of is an additional complication you have to deal with in remote sensing. If you're trying to do the remote sensing of water, there's a whole lot into all of this, of course. Let's take a look here at green vegetation. It's got a very interesting spectral reflectance curve. Let's look at what's going on with vegetation right here in blue, green, and red. Okay? I mean, what color do we think of vegetation being? If you walk outside, healthy vegetation is green. Well, why is healthy vegetation green to us? Because it happens to reflect a lot of green light, and the green light bounces into our eyes when we look at a tree or look at the grass or something like that. So you can see that going on right here. How much blue reflectivity does a tree have? Fairly little. How much red reflectivity does it have? Well, actually a little bit more than blue over here, but not a whole lot. We see this peak right here in the green area. So that's why vegetation looks green to us. You know, it hits us with green. But look at what happens to vegetation as soon as you get outside of the visible spectrum and go over here to infrared. It's probably a good thing that we don't see infrared light reflectivity, because if vegetation would just bombard us with infrared reflectivity. Healthy vegetation, I mean, this is how much we think of vegetation being very green. Well, here's the reflectivity of green. It's several times the reflectivity in the infrared. So that's why when we go to that false color composite and we're trying to detect vegetation, healthy vegetation, it makes it really easy to detect it if you can use near infrared. And then dry, bare soil. But if you are trying to detect something in remote sensing, you tend to look at a lot of these different curves. I mentioned last class about the professor at the University of Alabama who I took remote sensing with, who was doing the remote sensing of water quality, and he had a lot of these curves. He knew the particular kind of algae that he was looking for. So what he wanted to know was what is the spectral reflectivity of this particular kind of algae in the particular kind of water. And of course, in his remote sensing lab, he had a spectroscope, and he was showing it to us, that takes, it wasn't large, it would sit on this table, the one that he had, and then it's got this emitter at the top, which bombards whatever it is that he puts down under it with electromagnetic radiation, and then immediately records what is bounced back. So if you want to find out what's the spectral reflectance curve of, whatever it is you're looking for, he brings a sample of it into the lab, sticks it under the spectroscope, and it generates this curve for him across the entire spectrum. So if you're looking for concrete, or you're looking for, whatever it is, you put it under there. I mean, this is generalized because, okay, green vegetation. But what if you're looking for specifically cypress tree, or oak tree? Well, you would probably bring in your, very specific sample of your, your type of vegetation and get the reading on it. And of course, that's laboratory conditions. Under laboratory conditions, this particular thing that I'm looking for has this particular spectral signature. And then enter all the complications about bouncing through the atmosphere and everything else they have to deal with in remote sensing. But then how does this help you? Well, even this should give you an idea. If you're looking for healthy vegetation, as I said, well, it's a good thing if you've got a near-infrared band. And you can say, well, if I really want, if I'm trying to find every pixel, I'm trying to find everywhere where there's healthy vegetation, as a simple example, you might say, if this is the near-infrared band, computer, go find every pixel that has, in the near-infrared band, a reflectivity of this. Go over to the red band, whatever this reflectivity it is, find it in that band. Reflectivity of this in green, reflectivity of this in blue. And the computer will go and do that for you. It'll look through, all of these bands are of course geo-registered, so they've got pixels all stacked up on top of each other. And then the computer, you tell the computer, look, for every pixel that has this value in near-infrared, this value in blue, this one in green, this one in red. And then if you know the spectral reflectance of their substance, you can pretty accurately pull out which of those pixels probably contain what it is that you're looking for. Okay, that's why this curve is important. And then the more detailed you're able to do this, like, I don't know any specifics about different trees, but, it's probably the case that, elm and oak may be pretty similar. I mean, they're both going to be green vegetation, but it's probably the case that if I'm able to have a very high spectral resolution and continue to chop this up into finer and finer little levels of the electromagnetic spectrum, I may be able to find, aha, I can distinguish an elm tree from an oak tree based on this little sliver of the green band, where the oak tree is 12% more reflective, or something like that. And of course, that would be difficult to do by hand, but you can have the computer search for that across very large data sets fairly easily, of course. So that's why I say that if you're looking for something in whatever it is that you're doing, especially a lot of environmental sorts of things, if you're studying something that can be detected like this through studying spectral reflectance, then you can probably find it. You find yourself with a whole bunch of data. Let me see if I can find. I got another example that I like. Let's take a look at the first image here. Display unmute. This is some material that was taken from, I think, may have been taken from plane or helicopter or whatever. But it's a great sort of example when you're trying to find stuff out. Let's look over here. This is a true color composite here. Is this football field turf or is it astroturf? Is it grass or is it astroturf? Yeah, I mean, but here is very difficult to tell. I mean, that'd be a very difficult judgment because it looks green. I mean, here we got grass, here we got grass here. But what do we know about vegetation? We know that it is highly reflective in the infrared band. So then you switch over to infrared. This one is swapping out. In fact, this one may be what you were asking for. What happens if I leave blue and green alone but just swap infrared to red? I think that's actually right here is what we get. Now it becomes obvious. All of the vegetation went boom, red, easy to pop out. But look what didn't happen to the football field. Okay, so now it becomes very, very easy to see that this is astroturf. This is not natural vegetation. And there are, of course, a lot of applications for this. You know, being able to find all kinds of things. Also, like military applications. When you talk about like camouflaging different equipment or installations, and okay, you camouflage it so that it looks okay green or something like that, but then you might not have camouflaged it in the infrared. What if your equipment still reflects infrared light differently than the surrounding area? Well, if all you're doing is looking for whatever it is with your eyeballs, maybe you'd never know it, but then as soon as you fly something over that's collecting infrared reflectivity, if it's not infrared camouflaged, it may be very easy to distinguish from the surroundings.